At about the same time that Schrodinger was developing his wave equation, another scientist, Werner Heisenberg, was working on developing a quantum theory of matter. Heisenberg, one of the actual founders of quantum theory, developed what he called the uncertainty principle in 1927. Heisenberg said that if the electron behaves simultaneously as both a wave and a particle, as had already been deduced, that we can't divide the physical objects as either particles or waves. So essentially what this means is that if a particle can behave as a wave or a particle, then we can't separate their existences. We can't say, well, it's just a particle or it's just a wave. It's both. And so applying this idea to position and momentum, the uncertainty principle says that it is not possible to measure both the position and momentum of something with indefinite precision. And what this means is that while measuring things at a macroscopic level, we can have a very, very precise idea of their momentum and their position. We can measure its speed, we can see where it's at, and the only thing that limits us is the precision of the instruments that we use to make measurement. When we deal with things on a quantum level, there is a limit to the precision with which we can measure these two quantities. And this has nothing to do with the actual measuring devices. It's not because we have crude devices or because there's errors in the devices. Heisenberg said that it is a fundamental property of nature, and that there was a relationship between the uncertainty in the two measurements. And it's given by the equation we see here. What this tells us is that there is a limit to the precision of the combination of the two measurements. So we can become more and more precise about how much we know about the momentum of an object, of a particle, but in that increasing of precision related to the momentum, we must have a decreasing precision in the measurement of the position. So the more that we know about the momentum, the less that we know about the position, and vice versa. The more that we know about the position, the more accurately we measure the position, the less we know about the momentum, or the less accurate our momentum measurements become. And so if we take this to the extreme, that means that if the uncertainty in one of the measurements, say the position, is 0, then that means that the uncertainty in the other one has to be infinite. So let's try and explain this as simply as possible. Let's imagine that we take a beam of electrons and we shoot it through an opening. And let's say we have a very, very fine beam of electrons and we have a very, very small opening that has a size of A. If that opening is very, very small, then that means we know with a very high amount of precision, or very accurately, where the vertical position of the electrons are, because the uncertainty in the vertical position cannot be any larger than A, the size of the opening. But if the opening is the same size as the de Broglie wavelength of the electron will diffract similar to waves of some wavelength when passing through an aperture of that particular wavelength, or the size of that particular wavelength. So there's some specific uncertainty about the momentum because of the change in the direction. Remember that momentum is a vector, and so the direction of travel affects the object's momentum. And so as we get a smaller opening, the diffraction is going to increase, which means that the angle of spreading out is going to increase, and so there's much more uncertainty in the direction of travel, which means that there's going to be more uncertainty in the momentum. We can also look at the uncertainty principle in terms of energy and time. And so if a particular state is said to have, or is measured to have, some specific energy where the uncertainty is delta E, then there must be some uncertainty delta T in that time during which the measurement was made. And again, you can see that it's that same type of relationship as there was with the uncertainty in momentum and position. And it's greater than or equal to Planck's constant divided by 4 pi. See, that's a constant. It's Planck's constant divided by two constant numbers. And so if our measurement of the energy of an object, if the uncertainty in the measurement of energy decreases, then the uncertainty and the time must go up and vice versa. So to kind of sum up the uncertainty principle, what it says is that there's only so much information that we can truly know about a particle because of this idea that at any time it's both a wave and a particle, or it has both wave and particle-like properties. If we know more about the momentum of the particle, we're going to know less about its position and vice versa. As the uncertainty in one measurement goes down, the uncertainty in that other measurement has to go up to maintain that constant balance.